So we should pay attention to the low pressure systems once again, because we mentioned many things. We didn't look at the models and the difficulties of capturing LPSs in models. So when we talk about LPS, we already said that there is a tendency for the number of LPSs to be significantly large, 3 times larger or more during an active period compared to a break period. We also, and they bring about 60% of the rain over the core monsoon zone and maybe 40-50% in other regions. The genesis regions are important on each year, as well as impacts due to climate modes like the El Nino, Atlantic Nino, and so on. The tracks are important, and the amount of rain they bring are important. So the other thing we said in the context of the trends is that the episodic extreme events in break periods have increased, so the intensity of rainfall in active periods from 10 to 60 days, so 10 to 20, 20 to 60 days has decreased, whereas if you look at synoptic scales of 3 to 9 days, then they can be any in active or break periods, so they have increased. So overall the LPSs probably are bringing more rain, and there is a whole debate about whether there is a downward trend in the LPS or not, and it depends on the methods used. Then it makes it even harder to look at models to see model rendition of the LPS. You have to develop the model metric that may be different than observational metric. So you are looking for models whether they can reproduce the statistics of LPSs that we get from observations. Okay, and for projections you want to worry about the trends and other things. So let's look at a few results from 2 papers. This is from Bala and his group at COS at IISc, listing criteria considered by different algorithms to classify LPSs into lows, depressions, and deep depressions. So you have lows, depressions, deep depressions. This is the Bill Boos group and IMD archives, and Bill Boos is working on depressions and so on to see whether the trends reported from data are real or not, and what the processes are in terms of the vorticity, advection, and so on and so forth. So here sea level pressure anomaly is 2 to 4 hectopascal in the lows, 4 to 10, so deeper in depressions, and greater than 10 in deep depressions. Winds at 10 meters for the lows, there is no criteria, only the pressure criteria is used, whereas here they have 8.5 to 13.5 meter per second and greater than 13.5 meter per second here. Obviously if they go beyond 17 meter per second, they should be classified as tropical cyclones, which typically don't occur during the monsoon season because of the vertical shear, as we already mentioned several times. There is an automatic tracking analysis using the geopotential height criteria, which uses different parameters. So here geopotential anomaly at 850 hectopascal is used, less than minus 120 meter squared per second squared to minus 250 meters squared per second squared. So the anomaly is obviously low pressure cyclonic system. Geopotential height anomaly would be negative. Under depressions it's minus 250 to minus 500, but now you also have wind speed criteria of 8.5 to 13.5. For deep depressions they are deeper than minus 500 meters squared per second squared in the geopotential anomaly. And in the winds it's greater than 13.5, which is similar. When people look at doing this from models, this is from a paper by Andy Turner's group, which looked at S2S forecast models, so subseasonal to seasonal forecast models, to see how models do the forecasts of low pressure systems. So they have a detailed algorithm to go through and find the tracks and retain them or reject them based on these various criteria. So apply the feature tracking algorithm over all hindcast files of an ensemble member of an S2S model and retain tracks longer than 3 days. So there is a persistence time scale. Do all track points feature a negative mean sea level pressure anomaly or temperature anomaly less than 0.5 K at the center at 925 hectopascals, so closer to the surface, and so on. I won't read all of them, but you get the idea. Then the Andy Turner's group, I think Deoras was the lead author. They looked at the number of low pressure systems per season. So this is the seasonal average numbers of monsoon low pressure systems in all ensemble members of 11 S2S models in the green colors here. The Mera reanalysis product in the royal blue, and this is the multi-model ensemble of these models, and this is the ERA reanalysis. And you can see that the two reanalyses are fairly close with ranges that are slightly different, a larger range in Mera than in ERA, but the models are all over the place, and the multi-model ensemble is much lower than the either of the reanalysis. Doesn't mean the reanalysis are right or wrong, but it's just that these are data simulated products, so you can trust them more, and we know more about the model biases as well. So looking at the number of data points that tracks matched with ERA, so here ERA and Mera are used for forecast skill estimates for the different models here. I won't go through which model is which, but just to get an idea of how models do. So the number of data points and the lead forecast days, you can see that with ERA and Mera, at short lead times in days, the number of data points matching is high and quickly drops off with lead time, which you would expect skill drops off. But surprisingly, the drop off with Mera is different than in ERA. So the difference that is here is exaggerated here in the forecasts somehow. The position error, again, compared to ERA, there is slightly larger range of position errors as you go as the lead times increase, and they are more tightly bound to each other compared to the comparison with Mera, for whatever reason. So the intensity in terms of the lowest pressure, the bias in intensity, again, negative versus positive. Mera captures most of them being negative here, whereas compared to ERA, they are all mostly positive with one. That's the HMCR going here. So the observational estimates themselves are not always consistent with each other, and people have done comparisons of different products for LPSs, and there are differences. So obviously identifying them and tracking them is problematic even from data, but for the models also reproducing their genesis, numbers per season, interannual variability, tracks, deviation from the observed tracks, amount of rainfall, and so on are all a challenge. But as we said, we want to look for the statistics. So to look at the statistics, you look at things like this. You are looking at difference in daily precipitation in the JMA model, ECC and KMA model, and the UK Met Office models. So there are multiple comparisons. So JMA, ECCC, KMA and UK Met Office, and it is comparing the For every model, the difference is calculated as model precipitation minus GPM global precipitation mission precipitation estimates for all days. So 0 to 3 days, 12 to 15 days in the center. So this is all days, 0 to 3 days, and during days 12 to 15. Okay, and low pressure system days and LPS days and non-LPS days. Okay, so geez, complicated. Nonetheless, I just want to show that the validation has to occur in terms of the rainfall, the correlations with the total rain and LPS days and non-LPS days. So numbers indicate pattern correlation coefficient between LPS days and all days, non-LPS days and all days. So you can see that these correlations are typically high. These correlations, pattern correlations, are typically low. So the non-LPS days rainfall distribution compared to all days is obviously low, but for LPS days it's high. Okay, but you can see that the patterns, the rainfall, the differences in rainfall for all days and 0 to 3 days and 12 to 15 days are not so systematic. So you can see that some models have a bias that's a negative, a dry bias. Some have positive bias during LPS days, and it can be reversed during non-LPS days. So here it's dryish during the non-LPS days, wettish during the LPS days here. So this is dry during the LPS days and compared to GPM, and it's wet during, so it's raining more during non-LPS days than and less during LPS days. So this is what we mean by the genesis region, the tracks, and the deviations from the observations and so on. But nonetheless, we are in the extreme rain topic here. So to look at the extreme rain, extreme events, daily precipitation greater than 64.5 millimeter at grid points or locations within 1,000-kilometer radius of the algorithm based on ATAGC LPS tracks. So the LPSs are typically a couple of thousand kilometers in size, so you want to use some spatial extent to see if the models or the tracking methods are producing rainfall within the decorrelation scale of the LPSs. This period is 1979 to 2015. So this is the total count, so the frequency of these extreme events. This is the annual frequency, and this is the ratio in percentage of the number of LPS related extremes to the total number of extremes. So if the numbers are high, especially over the core monsoon zone, that means most of the extreme events defined by 64.5 millimeter threshold occur within LPS days. Okay, so the total count frequency of LPS days is shown here. So you can see 160 or so during this period, and the annual frequencies shown here each year, how many such extreme events are happening. So more than 80% of the extremes observed at locations in central India occur when an LPS passes within 1,000-kilometer radius of the locations. Median track and obtained with the ATAGC method based on LPS tracks. So this is the median track. Okay, so the point I want to leave it is essentially that LPSs are very much a part of the extreme rainfall, and predicting them statistically seems possible in terms of pattern correlations, but there are biases in the models in terms of amount of rain, the genesis regions, the tracks, number of LPS days, which is also critical, and so on. But we have already seen that the relation between LPS numbers and days with El Nino is kind of low. So if these are stochastic synoptic events, then Can the S2S models predict them? Will increasing resolution help? Will coupling to the ocean help? And all those questions have to be answered. But in the meantime, obviously LPSs are important for extremes, their distribution and forecasting and so on as well. Okay.